In this video, we're going to look at two different velocity examples. This first example, we have a rock dropped from a 144-foot building, and its position in feet above the ground. So the position S of t, S represents position. So the position at time t is given by negative 16 t squared plus 144. T is time in seconds since it was dropped. So S, my output, is the position in feet. Part A of this question says, what is the velocity 1 second after the ball is dropped? And what we need to know is that velocity, v of t, is the first derivative of position. Velocity is a rate of change. So when we're dealing with s of t, we have a function that's telling us the position in feet at a time t. Now that rate of change, when we take the derivative, that is going to become feet per second. So velocity is the first derivative of position. So in order to find velocity, I'll start with my position function, negative 16 t squared plus 144. And if I differentiate that, s prime of t, that equals my velocity function. And using the power rule on each term, I have negative 32t plus 0. So the 2 times negative 16 gave me negative 32. Subtract 1, I have an exponent of 1, and the derivative of a constant is 0. So I don't really need to write plus 0. I'm going to take that away. So now that I have my velocity function, I can determine the velocity at 1 second or at 2 seconds. So v of 1 is negative 32 times 1, or negative 32, and v of 2 is negative 32 times 2, or rather negative 64. So now thinking about this, these two outputs, they represent velocity. And velocity is a rate of change. We are considering feet position per second. So both of these need that unit, feet per second, written behind it. Thinking about that negative value here, velocity can be negative, and that is indicating that this rock is falling. We have dropped it from the top of a building. And as it falls, 1 second it's moving 32 feet per second downward. After 2 seconds, it's moving faster, and that's because gravity causes acceleration. We have this negative 16 in a lot of our position and velocity functions, and that is imperial measurement system, feet per second, acceleration due to gravity. So that's a constant that you're going to see quite often. And because we are speeding up as we fall, we're accelerating, we have a higher velocity 2 seconds after it's been dropped. So when will this hit the ground? And then what is the velocity upon impact? So B and C go hand in hand because impact is when we hit the ground. So let's think about this. When will it hit the ground? What do we know? Do we know the velocity when this rock hits the ground? We do not. Do we know the position when the rock hits the ground? That we know. How high off the ground is the rock when it hits the ground? And the answer is 0. So when will it hit the ground? That means determine the time, when, the position is equal to 0. So S of t equal to 0. Once we know the time at which it hits the ground, then we can determine the velocity at that time. So if I come over here and I say, well, S of t is equal to 0, that's 0 equals my position function, negative 16 t squared plus 144. I can factor this, or I can move terms. So I've got, that will be positive when it moves to the other side of the equation. Positive 16t squared is 144, or t squared is 144 over 16. Taking a square root, t equals technically plus or minus the square root of 144 over 16, or plus or minus 12 over 4, rather plus or minus 3. So because this is a parabolic, it's a parabola function, we have two zeros, but we don't have negative time because we're dealing in the real world, not in Back to the Future with Marty McFly. So in this situation, t equals 3 seconds. That's when the ball, or in this case, we actually have a rock, hits the ground. So what is the velocity? That was my answer for B. What is my velocity upon impact? Well, impact occurs at 3 seconds, so I can determine the velocity at 3 seconds. So V of 3 is negative 32 times 3, or negative 96. Velocity is a rate. This is feet per second. So negative 96 feet per second. And that negative is, again, indicating to us that this rock is shooting downward. A positive velocity would mean something is traveling up. So remember, velocity is a vector. It has direction and magnitude. All right, let's just look at one other example in this video real quickly, and this is also going to be dealing with velocity. In this example, we have a ball thrown upward from the ground. We have a velocity of 64 feet per second. You'll notice that 64 is the coefficient of the linear term. So the velocity is 64 feet per second, and its distance from the ground, t seconds, is given by our position function s of t. So part A is really similar to that last example. Remember, we are given position, but we can determine how fast, or velocity, by taking the derivative of position. So for part A, the first thing we'll do is find our velocity function, and that's the first derivative. So using the power rule, I have negative 16. I'm going to pull that 2. I have negative 32t squared, subtract 1. That gives me 1. I do not need to write that one. And then the derivative of 64t is just 64. So if we're looking at its velocity at 2 seconds or 3 seconds, all we need to do is plug those values in. So v of 2 and v of 3. And performing those calculations, plugging in 2 for t, I get out that the velocity at t equals 2 seconds is 0. So at 2 seconds, we have 0 feet per second. And then the velocity at 3 seconds, plugging in 3 for t, I get out negative 32. So thinking about what we're looking at here, at 3 seconds, we have a negative velocity. What does that mean this ball is doing? That means we started traveling up, right? We were traveling up. We eventually had a velocity of 0, and then we started traveling back down. So if we think about negative 32, we must be on our descent. It has already reached its maximum. Let's look at the next piece here. After how long means find t. So after how long, or how long after the ball is thrown, does it reach its maximum height? So we want to find the time when this ball is at its max. So as I just said, we're standing on the ground, we throw the ball up, it goes up, 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 up. Eventually, it stops moving up, and it starts moving back down. Now, what do we know about when it changes direction? What is the velocity going to be right here at that max? The velocity is going to be 0 because we had a positive velocity going up and then we have a negative velocity going down. And when we change from positive to negative, we must pass 0. So this means find the t value when the velocity v of t is equal to 0. Well, we already have our velocity function here. So v of t, if I let that equal 0, that is 0 equals negative 32t plus 64. This is easy for us to solve. That's 32t equals 64, or t equals 2. So this is at t equals 2 seconds. We know the ball is at its max height. All right, and our last question here. The last question says, how high will it go? So how high? Well, we're dealing with time, velocity, and position. How high will it go? So for part C, what that is saying, if we interpret it, height is position. We're looking for the position when we are at the max. And when does the max occur? At t equals 2 seconds. We just found that. So what are we going to plug 2 back into? We don't want to plug it into the velocity function, because if I plug 2 into the velocity, I get out 0. I want to plug 2 into my position function. So my position function is s of t equals negative 16t squared plus 64t. So s of 2 is negative 16 times 2 squared plus 64 times 2. That is negative 64 plus 128, or 64. 64 what? Well, we are dealing with position, and in this problem, position is measured by feet. So it reaches a max of 64 feet high at t equals 2 seconds. And if you were to graph this position function in your calculator, you'd get something that looks like this. And right up here, this ordered pair, if we were dealing with t, s of t, that ordered pair at time t equals 2, my position, my output, is 64. So you'd see that point show up as the maximum on your graphing calculator. And if you draw the tangent line, remember slope is rate of change and slope represents the direction of that tangent line. The tangent line there, we'd get a horizontal tangent line. Remember, the slope of a horizontal line is 0. So this should all be tying in together and making sense. As always, if you do have any questions about these problems, please feel free to get in touch with me, because I would love to be of service and help you understand them better. Thanks for listening, and have a great day.